All right. We're going to start with 3 data points. That's all we're going to need today. Y2, oops, Y1, Y3, X1, X2, X3, Y1, Y2, Y3. And we're going to think about a common task, which is fitting the data, in particular fitting with a line. So let's say, consider fitting with a line. So what does a line involve? Let's see. You have to have, well, you only need 2 numbers. You need an intercept. We'll call that B0. And you need a slope. We'll call that B1. And let's actually, oh, I'm getting these notices again. Oh, well. Let's actually just kind of sketch a line. All right. We're going to fit with a line. Maybe it'll look something like that. Well, we haven't really determined what line we want to pick yet, but whatever line we pick is going to have an intercept and a slope, and that defines the line, and it's going to create residuals which are the differences between the line and the actual data points. These are predictions. Oh, let's see. The line predicts points. Let's say that first. The line is going to predict points. It's going to make a prediction for y2. If x2 is here, the line predicts that y2 should be here, and instead it's right below. All right. And if x1 is here, the line is going to predict y1 to be here. And if x3 is here, the line is going to predict y1 to be here. And there's going to be a mismatch at each point. All right, there's going to be a mismatch between the predictions and the actual values, and those are called the residuals. So let's say it creates predictions first. Creates predictions, and it predicts y1 by b0, the intercept plus the slope, times x1, y2 by intercept plus slope times x2, and y3 by intercept plus slope times x3. And so it creates predictions, and then the predictions create residuals, the mismatches. And they are, well, what are they? They're each y value minus the predicted value. B0 plus B1 x1, y2 minus B0 plus B1 x2, y3 minus B0 plus B1 x3. All right, so you've got predictions and you've got residuals, the differences between the observed values and what your line would have predicted the y value to be. And what's a common line that people like to use in particular? I said, any line is going to have some slope and some intercept. There's a particular line that people really like to use. Anyone want to tell me what line I'm thinking of? What's the name of a common line for fitting data?
A constant.
Constant. Well, you could use the same number. That's the most basic thing to use. But if I want to use any line, that would be like a horizontal line, right? But if I just want to use
fit?
Say that again. Best fit?
Line
Yeah.
of best
Well,
fit?
yeah. What's another name for what people usually When someone says the line of,
Minimizing the sum of squares.
yeah, well, that's the criterion. Yeah, I think the name for it I would use would be the least squares line. So yes, the least squares line, the line that minimizes the sum of squared residuals. All right, so let's think about that. Let's just write out what that means. Let's write out what that means. The least squares line, in particular, the least squares line is defined to be the line that minimizes the sum of squared residuals. Minimizes sum of squared residuals. And in particular, let's just write that out. What does that look like? That's the sum over all the data points of the response value, all right, minus the predicted value, b0 plus b1 xi squared. All right, so this is maybe review, and this is the way we usually think about it. We usually, or what you're used to, is seeing the scatter plot picture. You know what? Let me draw my response values one more time so they're not covered up by the orange arrows. Okay, so we're used to seeing a scatter plot and thinking about lines fitting data, and in particular, a commonly used line for fitting the data is the least squares line. But I want to introduce in this course and starting today an alternative way of thinking about your data. So let's see. We're going to think about this. We're creating predictions. We predicted each observation separately. Y1 by its x value evaluated at the line, y2 by its x value evaluated on the line, y3 by its x value evaluated on the line. I want to rewrite this stuff. Actually, let me do some color here. We're gonna rewrite these statements. Instead of thinking about the observations, right? Right now I've got a separate line for each observation. Now what I want to do is instead think about these ideas in terms of vectors. So instead, here's what I want to write. I want to say, we can write predict the response vector y1, y2, y3 by prediction vector b0 plus b1 x1, b0 plus b2 b1 x2, b0 plus b1 x3. All right, this looks kind of neater. We only have one sort of pair of things that we're comparing instead of three pairs of things that we're comparing. But is that really helpful? Well, let's also just kind of expand this out a little bit more. We're going to call this guy bold y. And let's expand this out. What if I write it like this? B0 times 1, 1, 1 plus B1 times x1, x2, x3. Is that the same? That's another way of expressing our prediction vector. And let me also give shorthand names for these guys. So these vectors, I'm just going to use bold 1 and bold x for these vectors. So the y vector is predicted by some number times the 1 vector plus some other number times the x vector. That's the set of possible predictions we're thinking about if we're predicting each y value by using a line. What do the residuals look like? What do the residuals look like? All right, let's see. Let's do another arrow for the residuals. And we get a residual vector. residual vector. And what does it look like? Well, it has y1 minus b0 plus b1 x1, y2 minus b0 plus b1 x2, y3 minus b0 plus b1 x3. All right, there's our residual vector. Just has three numbers. And actually we can write it, let's write it more simply. Let's write it as y vector minus b0 number times 1 vector plus b1, that's a number, times the x vector. So there's our residual vector written out as basically a linear combination of vectors y, 1, and x. And, well, let's keep going. Let's think about the least squares line in terms of vectors. And this is where the payoff is going to start happening. All right, minimizing the sum of squared residuals. You know what? Let me draw the arrow from this guy. Sum of squared residuals. These are the sum of the squared entries of the residual vector. Can you see that? See the residual vector here? The entries of the residual vector are exactly the things that are being summed up and squared and summed up in the quantity called the sum of squared residuals. So let's write the sum of squared residuals as the squared norm of the residual vector, right? This is the sum of the squared entries of the residual vector, and so is the squared norm if the of the residual vector. By definition, the squared norm is the sum of the squared entries of a vector. All right, now that's going to be crucial. That's going to be crucial. Let's see if we can figure out why. All right, first step is to draw another type of picture. So we've got the scatter plot. That's the usual picture of our data. But we rewrote all of these aspects of our data that are relevant. We're fitting with, we've got these prediction vector. We've got residuals created, and we've got the sum of squared residuals is the squared norm of the residual vector. And let's devise another picture that actually is going to make all of that much more intuitive and useful. So here's another picture I can draw. All right, there's a z-axis and a y-axis and a x-axis. All right, if you've seen a 3D plot, this is supposed to be, this line is supposed to be coming out of the screen at you, all right? And then receding into the screen, and maybe these two are in the plane of the screen. All right, so this is R3. And what space do these vectors that we've been talking about live in? Y and 1 and x. What space do these vectors live in? Well, y is y1, y2, y3. 1 is 1, 1, 1. X is 1, 2 is x1, x2, x3. These are all vectors in R3. Let's kind of sketch them out. Let's add them to draw them in this picture. All right, so we've got a 1 vector. I'm just going to kind of make it sort of pointing maybe out at us. All right, there's the 1 vector. The 1 vector right there. Man, that's ugly. Okay. I got to get better with this pen. What else do we have? We also have an x vector. I'm just going to kind of make him point over it here in just some arbitrary direction, basically. He's kind of pointing away from the screen, let's say. And we have a y vector, y1, y2, y3. Let's just stick him kind of like that. There's our y vector. All right, So how does that help us? Well, let's think a little more about what the possible values of the prediction vector are. What are the possible, let's write that. What are the possible prediction vectors? Well, they are the set. Let's go back and look. All right, we're allowed to pick. Here's what the prediction vector looks like. We're allowed to pick any number b0 or b1, and then we're going to get that linear combination of the vectors 1 and x. So what are these possible prediction vectors? They are, let's write them as b0, 1 plus b1, x for b0, b1, in R. Pick any real number b0 and b1, and that linear combination of 1 and x can be a prediction vector if you're fitting with a line. There's another name for this. There's another name for this set. What am I thinking of? The name for every possible linear combination of 1 and x. Remember your linear algebra here.
Span.
Span, bingo. The span of 1 and x. All right, let's kind of try to depict that in the picture a little bit. Let's just kind of, I'm just going to kind of draw some horizontal lines and just say, there's a plane created by 1 and x. I just threw some horizontal lines in between the two vectors, but think of it, it's not just, in between those vectors, it's the entire two-dimensional plane that those vectors live in. That's the set of possible prediction vectors. Okay. And now let's look back at our criterion here. We want to minimize the sum of squared residuals. So just based on rewriting the sum of squared residuals as the squared norm of the residual vector, what do we want? We want, really, it's y minus the prediction vector. And so what we're saying is if we want this to be as small as possible, we want the prediction vector, this is the squared distance from y to the prediction vector. If we want this to be as small as possible, then we want the prediction vector to be as close to y as possible. All right, for least squares line, prediction vec should be as close to y as possible. All right. That's how you minimize the sum of squared residuals. The sum of squared residuals is the distance from the prediction vector to the response vector. So minimizing the sum of the squared residuals means getting as close as you possibly can to the response vector. You want the squared distance, or the distance in general, to be as small as possible. So there's actually a name for that, but let me just write that as a note. Which vector in this subspace of span 1 and x is closest to y? Does anyone know the name of it? This may be something that was covered in your linear algebra class. There is a unique vector in the span of 1 and x that is closest to y, and it is called the
Projection.
Yeah. Technically, the best term is orthogonal projection. When someone says projection, they mean orthogonal projection usually, but there is something called oblique projection. So I'm always going to hopefully use the term orthogonal projection, but yes, it is the orthogonal projection. So you have to, let's see, what do? You need to go orthogonally down, and you need to hit this span And let's call the resulting prediction vector y hat. You need to hit this span orthogonally. All right, you need to create a right angle right there. That's the answer. That's the answer. Which vector is in the span of 1 and x is as close as possible to y? That is the prediction vector that that results in the smallest sum of squared residuals. So the answer is the orthogonal projection of y onto span of 1 and x. And we're going to call that y hat. So it has coefficients of 1 and x that produce y hat. So the coefficients, let's draw that. Let's draw that first. Let's see, what do we have here? We've got there's some linear combination of the 1 vector and the x vector that leads to y hat, that makes y hat be the prediction vector. And what is the one term? Well, it's going to be let's say b0 hat is the coefficient of 1 that's needed. And let's say b1 hat is the coefficient of x that's needed. And together, those lead you right to the orthogonal projection. I mean, we don't know what those coefficients are, but at least we're zeroing in on them. We know a lot about them. We know that they're the coefficients of 1 and x that lead to the orthogonal projection of y onto the span of 1 and x. So that's going a very long way toward figuring out the slope and intercept of the least squares line. So I'm going to go ahead and write the coefficients of 1 and x that produce the least squares prediction vector y hat are exactly the intercept and slope of the least squares line. Well, another way of saying that is y hat equals b0 hat 1 plus b1 hat x. Whoa. I'm dragging something. I didn't mean to do that. Let's see if Control Z works. If the least squares prediction vector is this linear combination of 1 and x, then y equals b0 hat x plus, b0 hat plus b1 hat x is the LS line. b0 hat plus b1 hat x is the least squares line. You just need to use these same coefficients. The coefficients of 1 and x are exactly the same as the coefficients of the intercept and slope of the least squares line, because it produces the smallest sum of squared residuals. So this is not a bold y and this is not a bold x. These are just dummy variables defining the line, y and x right here. All right, and here these are bold. Let me just maybe reinforce that. These are the bold ones. These are the x vector, y hat vector. All right, and these aren't bold. All right, and the important thing to notice here, is that This is not limited to sample size 3. Not limited to sample size 3. The reasoning that we just went through and the picture that we just drew even, they work in general. Let's write that. The reasoning and picture work for arbitrary sample size n. And well, why can I say that? I mean, here I had y and 1 and x were vectors in R3. So I drew a little depiction of R3 and I stuck some vectors in. You know, there's nothing weird about that. But drawing Rn, how do I draw vectors in Rn? How do you draw Rn? You don't have enough. I don't think you can, as far as I know. But that's not really a problem because 1, all right, 1 and x and y inhabit a 3-dimensional subspace of Rn. Why do I say that? What's the dimension? Whoops. What's the dimension of their span? What's the dimension of the span of 1, x, and y? Actually, what's the largest possible dimension of the span of 1, x, and y? 2.
3.
Yeah. If I have 3 vectors, I'm taking every possible linear combination. That's at most a 3-dimensional subspace. So there's a 3-dimensional subspace of Rn that has 1, x, and y, and we're just saying that's what we're going to draw. You can draw a 3-dimensional subspace of Rn, and everything is going to work just fine. So that's just, imagine that's what we're drawing. In general, I'm going to be not sticking with cases where I only have 3 observations, and instead of R3, I'm going to write Rn. And it's still going to be legitimate. It's still going to be perfectly legitimate drawings. All right. So let's see what we've got here. All right, let's keep zooming. So I have names for these types of pictures here. Let's see. I say one of them is the observations picture, and the other is the variables picture. But let's write it.
Why is it a 3-dimensional subspace?
Why is what?
Why is you just said that the 1 vector, x vector, and y vector inhabit a 3-dimensional subspace. Can you just go for y again? Sorry.
Yes, because they are a basis for their span. And dimension means the size of the number of vectors it takes to have the number of vectors in any given basis of the subspace is a span. So that's a little bit abstract from an abstract idea from linear algebra. That'll actually be in the book if you need to review that. But in general, if you have any subspace has a basis, and the number of has infinitely many bases actually, and every basis has the same number of vectors, and that number is called the dimension of that subspace. So 1 and x and y are a basis, or if anything, they could be, if one of them is a linear combination of the others, then it's actually going to be, fewer dimensions. The subspace is going to have fewer than 3 dimensions. So it could have fewer than 3 dimensions, but we'll just say it has at most 3 dimensions. It's at most 3-dimensional subspace of Rn. And there's really no problem at all in drawing pictures. Drawing a picture and writing Rn and having 3 vectors in Rn, and what you're seeing is just a 3-dimensional slice a three-dimensional slice of Rn, just like you can draw a two-dimensional slice of R3. You know, if you have, you know, vectors in R3, and you just sort of slice through with imagine slicing through with a knife or something and getting some little plane of where you sliced. You know, you could draw that on a two-dimensional plane and act like it's just a, you know, an XY plot. And you can do the same thing in terms of drawing a slice of Rn, a three-dimensional slice of Rn. All right, does that help?
Yes, thank you.
All right. Observations as points versus variables as vectors. All right, and let me clarify something. When you have an actual data set, when you have an actual data set and you're trying to make sense of the relationship between variables, this observations as points is the right thing to draw. Draw a scatter plot. You have data, you have two quantitative variables, draw a scatter plot. You're never actually drawing this for real data. This is a generic picture that informs us regarding linear model theory. This picture guides our intuition and understanding of linear model theory. It's not supposed to be an accurate depiction of a particular data set, and it's not particularly informative for a particular data set. No one ever draws this. No one ever gets, you know, hops into R and someone gives them some data and they try to draw this. They draw scatter plots. For understanding actual relationships and actual data, you draw observations as points. For understanding linear model theory, usually the more informative picture is this, variables as vectors. So we're going to try to get really good at thinking about things in this way, thinking about the variables picture. Now, it's counterintuitive. It takes some time. I mean, I've sort of refined my drawings a little bit, and I think it's manageable. And you may think that you already have it down perfectly, and maybe you do. But in general, this is not the intuitive way of visualizing your data. Observations as points is very intuitive. Variables as vectors take some work to become comfortable with, usually. So that's our challenge. I gotta figure out how to. All right, so that's our challenge, is understanding variables as vectors. And furthermore, it turned out that basically the most important question of least squares fitting reduces to just orthogonal projection, which is just a pure linear algebra topic. And that's actually going to be an important aspect of the way we cover this course, or cover the material in this course. There's so much of linear model theory just turns out to be very easy if you have a solid foundation in orthogonal projection and other topics from linear algebra, and a solid foundation of dealing with random vectors as well, and with normal distributions. So I'm going to focus a lot of energy on that sort of foundational material. We're actually going to take probably about 3 lectures worth of a break from this, from least squares fitting, really, and from data analysis. We're going to take a 3-lecture break and cover aspects of linear algebra, starting with orthogonal projection. And so I'm going to say, I can call it a review. It's sort of review, but I don't think you should expect that you understand everything that's going to be covered as well as you should. So please don't think that this is, something that is going to be too easy. Some aspects of it probably will be, but some aspects of it are probably things that weren't covered quite as in depth as I want them to be when you're in your previous linear algebra experience. And also, I have so many students who at the end of the semester, they say, I didn't really learn linear algebra very well the first time through, and I really feel like I've got it mastered after this course. So that's actually that's another reason that I try to cover it thoroughly, because not only does it just make the linear model material much easier, and it also just is basically linear algebra is the single most important foundation for any quantitative application, as far as I can tell. More important than calculus, more important than just sort of any other of the basic foundational classes that you take. And in my experience, at least, maybe people differ. I hate calculus, so I'm biased. I love linear algebra. I hate calculus. And actually, there are a lot of things that you can do with linear algebra that you otherwise would use calculus to do, but there's some clever way of doing it in linear algebra. And actually, one of them is doing least squares fitting. You're trying to minimize something. You'd think, oh, okay, that's a calculus problem. I'm trying to minimize this function, so I need to take some derivatives. But taking derivatives when you've got vectors is kind of ugly. It's fairly ugly as it is in my opinion, but it just gets really ugly. And the idea that you can draw pictures and just sort of have geometric intuition for how to solve these things instead is I love that. So anyway, linear algebra is my favorite foundational topic, and I truly think it's the most important. So I really want to hit that hard and emphasize that. And we're going to spend probably 3 lectures on crucial features. And I'm not going to go way back and cover everything from the ground up. Actually, the book does do that. So if you really need that, if you really need to start over, or if you want to just have maybe a more abstract and more thorough understanding of linear algebra, then you can read the whole first chapter of the book, which I'll release the book on Wednesday. But the lectures are going to be a lot more focused than the book in terms of what to focus on, really needing to know from linear algebra.